Hi, everybody. We're going to talk a little bit today about sequences and series. The main thing is I want to get a little more rigorous about talking about the limits of both sequences and series. So first of all, remembering that if you think of a sequence as a function whose domain has been restricted, it's been restricted so that the x values are natural numbers. That'll be kind of the best way to think about this. Suppose you have a function that has a decent limit as x goes to infinity. That is, the limit as x goes to infinity of f of x equals some number. Let's call it L for limit. Then that means the corresponding sequence, that is just the values of this function restricted to natural numbers as the inputs, also should be equal out. In a sense, it's just changing the name of the variable, but it's also thinking of the sequence in place of the function. And you should think about this sort of in a geometric way, I would say. The idea that the function approaches a limiting value means that the graph of the function maybe does some wild stuff at first, but eventually it approaches a horizontal asymptote. Well, that one didn't really approach it. Let me try that again. It's approaching that horizontal asymptote, right? So the y-coordinate of that dashed line is L. And this is the graph of our function f of x. Well, the idea for the moving from the function to the sequence is simply that the sequence is just particular spots along this graph. So that would be A0, and then here's A1, A2, A3, A4. Right? I'm basically thinking about integer spots along the x-axis and plotting the value there. And you see that, again, like the function, after this initial dipping funny behavior, it's getting closer and closer to a certain value. So these things started positive, then went negative for a while, but then they're just getting closer and closer to the value of L. So a consequence of the way we define the limit for a sequence is that sequence limits obey the same rules that limits for functions did. In particular, we're thinking about limits as you go to infinity. So that means there are limit laws for sequences, and honestly, these are all just reflections of laws we learned about limits previously when we were dealing with functions. So suppose we've got two. It's supposed to be an O. Suppose a sub n, which goes from 0 to infinity, and b sub n, these are two sequences. And that they have known limits. And so, for instance, the limit as n goes to infinity of a sub n is, say, L. And similarly, you've got a limit with the variable going to infinity for b sub n. And I'm just going to pick the next letter, L and L, okay? Then the limit laws, well, the first couple of limit laws just talk about limits being linear in the following sense. There's 4 of these limit laws we're going to talk about, but the limit of a sum is the sum of the limits. That's how you say the first law. So then, as n goes to infinity of the sum of a and n, a sub n plus b sub n, well, that's going to just be equal to L plus M. And if you expand it out, what L and M are, they're the limits respectively. So it looks like the limit of a sum equals a sum of the limits, right? Another thing, oh gosh, I probably need one more thing up here. Yeah, I do. Let's add a piece to this that I want to have a real number floating about. So C is an element of the reals. Why? Because the next law says that essentially that you can take constants out of limits. So the limit n go to infinity of C times a sub n, well, that would just be C times L. And again, if you expand out what L means, that's the limit of a sub n, so this looks like C has been pulled out of the limit and put out in front. Okay, so that's our first two limit laws. There's a couple more that are, no, I should. So the other two limit laws are ones that involve products and differences, products and quotients. So if you need the limit of a product of two things, again, it's going to infinity, so this would be a sub n times b sub n. Well, it works in the way you would hope, that you can just take the limits separately and multiply. And very similar, but with one slight tweak, is the rule for quotients. If you're taking the limit as n goes to infinity of a sub n over b sub n, you do get L over m, but you have to add proviso, and I think you can guess what it is. We're dividing by that lower sequence b sub n, so you need to know that m there isn't equal to 0. So I'm gonna just look at one of the things in example 1. This is on page 650 in your book. 3n cubed over n cubed plus 1. Just an example of using these rules. Now, okay, can we use, say, this rule up front? You might look at this expression and think, yes, you can, because it's got a an over a b of n. The an is 3n cubed, and the bn would be n cubed plus 1. But, you know, this whole thing is predicated on the idea that the limit of a sub n is L, and the limit of b sub n is m. That was the heading before any of these limit laws were expressed. Does the limit of 3n cubed even exist? No, sorry, that goes to infinity, as does that. Right? So this would be infinity over infinity if we tried to reckon it that way. Now, is there something we can do with it? Well, actually, I can tell you, the limit here is 3. You can always tell the limit of a rational function if it's got a degree in the numerator and in the denominator that's the same, then just compare the leading coefficients. So this would be 3 over 1. Right? And so we're in that scenario where the degrees are the same. If the degree of the numerator is larger than the denominator, then it blows up to infinity. And if the degree of the numerator is smaller than the one in the denominator, then it goes to 0. So those are rules that you learned with functions. The same thing happens with sequences. Yeah, the problem is that's just a heuristic, right? That you know, any sort of a monkey see, monkey do approach that you can deal with a rational function. I'd like to do this in a sort of more accurate way. So that is using some of our limit laws, and we can. I just need to modify things so that I have a ratio where the things have limits. It's just an algebraic trick. So if you multiply the top and the bottom here by 1 over n cubed, which, because n is going to infinity, it seems like you're multiplying by 0, but you're not, because it's as n goes to infinity. It's not there yet, right? So yeah, this is equal to the limit n going to infinity of 1 over n cubed, 1 over n cubed, and both top and bottom. The top still has the 3n cubed in it, and the bottom has the n cubed plus 1 in it. To group that, right? Of course, because of this, I mean, the reason I chose this is so that this top just ends up being a 3. The n cubed and the 1 over n cubed cancel each other. And then the bottom we get 1 plus 1 over n cubed. I guess I need to move to the top of the board. All right. So yeah, that's equal to the limit with n going to infinity of 3 over 1 plus 1 over n cubed. Now, I mean, if you really try to actualize what the limit laws say, it says that if you have a limit of a fraction, you should just take the limit of the top and the bottom, provided they exist and provided the bottom isn't 0. So this is the limit as n goes to infinity of 3 divided by the limit as n goes to infinity of 1 plus 1 over n cubed. Well, we know what both of these are. The top one, of course, if the 3 is just the constant value 3, it's not changing as n changes, so the top is 3. And what's the limit of this bottom? That one's really easy to see. You've got 1 divided by a number that's going to infinity. You know, this term goes closer and closer to 0, so we've got 1 over there. So that's 3. So originally I said I was just going to do one of these things, but I think it might be smart to do one other one. The part B of example 1 was a little bit hairy. So this one I just did was example 1, part A. So let's do example 1, part B next. Here the sequence B is called B sub n, and make sure I copy properly. It's n plus 5 over n raised to the n power. Crazy. So we're trying to figure out what happens to that. Limit as n goes to infinity of our B sub n. Well, I might as well just substitute what B sub n is equal to in this. Now there's a little bit of trickery I want to do to this. I basically want to define a new limit, a new function, a new sequence that is the logarithm, the natural logarithm of that, and see if we can figure out what's happening to that. Why would I want to do that? Because I got the variable in the exponent, and that's the trick you always do when you have the variable in the exponent. Right? Use logarithms to bring the variable out of the exponent. So let's give that trick a shot. Well, yeah, first off, let me just say that's what our question is. What is the limit of this thing? So we're going to define, I don't like to use the letter C. Well, why not? So C sub n is equal to the natural log of B sub n. Right? So what does C sub n look like? It looks like a natural log of that expression. N plus 5 over n raised to the n power. And I can use some of the rules for logarithms. Actually, I think I want to use a couple of them. No, just the one. Just get the n to come outside of the logarithm. Now, if we can figure out what the limit of this expression is, then my claim is we just take that and put it in the power on e, and you'll get b. So that is, if the limit as n goes to infinity of c sub n exists, you want to give a name to it, say it's equal to, we're always using L for limits, so let's use L again, say it is L. Then I can figure out what the limit of my original sequence was. The limit n going to infinity of b sub n is just going to be e to the L. So, you know, when could that potentially break down if L was giant and, or, you know, if L was going to infinity, this would still go to infinity. L could be 0 or not, yeah. So if we can figure out a limit for this new function, this new sequence, then we'll be able to just basically invert the function and get the limit for the original one we were interested in. So is that a good move? Well, yeah, I think it is, because I believe this expression has, it is possible for us to figure out the limit. The natural log part of this looks like that's going to a limit, because the part that's a fraction inside of here, well, actually, yeah. The sense of not even depending on n, I think, if you end up getting the natural log of 5 right there. But you can still think of it in terms of limits. As n grows bigger and bigger and bigger, the top is a giant number plus 5, and the bottom is that giant number, and their ratio just gets really, really close to 1 as n goes to infinity. So this piece goes to 1, but darn, n is blowing up. We can't use the product version of the limit law. But you can work with it still. So the limit n going to infinity of c sub n, instead of timesing by n, let me divide by 1 over n. That is, it's the same thing. I have to write that word limit a million times. Limit n going to infinity. We'll have the natural log of n plus 5 over n in the numerator, and we'll have 1 over n in the denominator. Now these are both, no, I've got a problem because that limit goes to 0 and I'm dividing by 0. Wow, it's worse than that. The top, oh sorry, the bottom is going to 0, and the top is also going to 0. You can re-express what's in here as, think about that, it's 1 plus 5 over n, right? So that guy is 1 plus 5 over n. What happens to that? This part goes to 0, and that part stays as 1, so we have the natural log of 1. But wait, that's a problem too. The natural log of 1 is 0. So we got 0 over 0. Oh, perfect. This is indeterminate. This is an indeterminate form. That's actually good news, because there's a named rule that we can use when you've got an indeterminate form. This guy looks like 0 over 0, right? So what is the trick you do when you have an indeterminate form? You use L'Hopital's rule. All right, so I just erased and then cleaned up and re-expressed the limit that we're trying to get now. And I hopefully, again, remember this looks like 0 over 0 as n goes to infinity. So use L'Hopital's rule and see what that does for us. Well, this thing is equal to the limit and going to infinity. I mean, what L'Hopital's rule says to do is take the derivative of the numerator and denominator, and you know, you can apply that a second or a third or a fourth, or you know, as many times as you need until it stops being 0 over 0. All right, so I'm going to work on the bottom first. We've been doing so much integrating, it's probably a little bit of a twist to go back and differentiate. That bottom is n to the minus 1, right? And when you differentiate n to the minus 1, you get negative 1 times n to the, subtracting 1 from that, minus 2. Right, so the denominator is negative 1 over n squared. What about the numerator? This is the natural log function. Its derivative is 1 over x. So you get 1 over 1 plus 5 over n. But that would be if it was just log of x, right? This is log of some u, and we need the derivative of the inner piece there too. We have to use the chain rule. All right, so what does the chain rule tell us? Well, we need the derivative of 1, well, that's 0, and then derivative of 5 over n, it's rather like the one we just did. So we get negative 5 times 1 over n squared. Yay, so I think this is all doable now. You see how there's a 1 over n squared and a 1 over n squared both in the top and the bottom? There's also two minus signs in the top and the bottom. What survives is this numerator and a 5. If we cancel those 1 over n squares. Okay, I just am having the hardest time getting the right number of humps on my m's. There we go. Yeah, so we'll have 5 times 1 over 1 plus 5 over n. Because this thing canceled with this thing and that minus sign. Yep, so we're down to a single fraction. Well, this is a particularly nice one. The top has a, well, maybe we should include this 5 into the numerator. The top is just a constant, so it's equal to 5, and the bottom is 1 plus, well, something that's going to 0, so it's 1. Right, so that's brilliant because now we know what our original guy's limit is. Right, this is the limit of c sub n, so the limit we're actually after, the b sub n, is that, well, is e raised to the power of that, u to the 5th. I just checked and the book agrees with me. So, all right, so that's a couple of examples of using limit laws. So I wanted to show you a couple of things from my screencast setup. One, this is a scan of page 650 from our book where the limit laws are written down. So, you know, I did put them on the board, but I just wanted you to have a reference to in the book where that happens. And the very first thing I started with in this section is about how you think about the limit of a sequence in terms of the limit of the corresponding function. So that's in the box there. There's also another scan that I've included here that includes some terminology about sequences, which I want to come back to in a second. But first, I want to use the calculator to show us something about that last sequence we dealt with. So, what have I done here? All right, so going to y equals, I had something old in there. The function we were dealing with was well, it had n's in it, right? But I'm going to replace those with x's. So it was, let's see, x plus 5 divided by x, and then that whole thing, well, that'll be misformed if I do it that way. I need to insert another parenthesis, okay? And that thing raised to the x power, to the x. Actually, let me check my table setup. We start at 1 and go by 1s, great. So hit our table, and you see the values of this thing. Now, 6, 12, 18, 25, 32, 43, 48. They seem to be growing kind of a lot. Are they sort of getting into control here? Not so much. I mean, they're still going up by 1s and 2s at a time. But I do see the amount that it's increasing has gotten a little bit not as extreme. They seem to be going up almost just one unit at a time. It's only in the 1s place that I'm seeing changes. Oh, there's an interesting moment. The first time when we had 2 times when the 1s digit was the same. Can you guys see this? I'm going to do a little zooming so you can see the screen better. Does look like there's another place, a 111, and then another 111, 112, 113, a couple of 113s. So maybe it's approaching something. Seems maybe it's sort of reasonable. I've been with the calculator. You can play with this a little bit. Change your table setup, and instead of starting at 45, maybe start at 200. Then look at what the table is telling us. 139.5, 139.6. Yeah, see now we get stuff that's, well, it looks like it just made it over 140. I'm saying it looked like it was going to go to 140. It's approaching a limit, but it's approaching it pretty slowly. I think it's going to get over 141 too. All right. What was the thing we actually determined the limit was? It was e to the 5th power, yeah? Well, 148.4. So perhaps it makes sense that it's, when we're down around 141, it's still climbing fairly rapidly. Try the table setup again and start it off much farther down the line. How about at 1,000? And look at the table. 146.58, 585. They're all 5.8s. Oh, there's a 5.9. And then I bet it stays at 5.9 for a while. There's a 46.6. Yeah, you get the idea. It's approaching this thing, but it's going to take a long time to get there. Okay. Well, but that's okay because we worked it out, with, what am I trying to say? We worked it out with math. Yeah. So we don't have to rely on just the numerics there. So what else did I want to talk about in this chapter? There's this box at the bottom of page 151 that we need to make sure we're all good with. Basic terminology for sequences. You say a sequence is increasing if the next term, the n+1 term, is always bigger than the nth term. That sort of makes sense. As you move to higher and higher values of n, it gets larger. So we call that an increasing thing. That, by the way, is exactly what we mean by functions, increasing or decreasing. Decreasing is the third one down here. It's weird that they say increasing and don't immediately follow it with decreasing. But there, the n+1 guy is smaller than the n. So they're giving examples of these things. That's great. What about non-decreasing or non-increasing? That just means the inequality is weaker. It's a greater than or equal in the one case and a less than or equal in the other. The word monotonic is a very useful one. It is used when you're either always going up, or at least not backtracking, or always going down. And again, not backtracking. So technically non-increasing or non-decreasing. So monotonic means, well, it's what it says here. It moves in one direction. One tone, I suppose. I don't know. We can also talk about bounds on a sequence. A function is bounded above, a sequence is bounded above if there is some number that's always greater or equal to the things. They've done this thing that I find annoying, is putting the quantifier after the thing. So for all n, a sub n is less than or equal to m, would mean m is an upper bound, or the sequence is bounded above by m. And there's a very similar definition for the words bounded below. If you've got both of those, there's a high limit on where you can be, there's a low limit on where you can be, then you're just bounded, period. There is a really nice theorem that we'll end with today that is called the squeeze theorem. And I think the best way to show you this is to do it on a graph. I do want to come back out and to get a wider view of the calculator. All right, so I'm going to give you three functions, one of which is a lower bound on the middle guy, another is an upper bound on the middle guy, and the middle guy is in between the upper and the lower bound. So we're going to put those into our y equals. Now, the functions I want to give you are the negative of 1 over x, the positive of 1 over x, and finally the sine of x. Yeah, just rethinking that a second. The sine of x divided by x. And I'm just gonna graph these. I don't know what. Oh my goodness, my window is kind of weird, isn't it? Yeah. After it finishes graphing the first time, I'll set the window up. All right. Let's put it in. Oh, I know. Let's use Zoom Standard number 6 under the Zoom menu. Actually, Zoom Standard is a terrible one to use because I want to look at this for positive integer values. So, how about this? Let's box zoom it to get the part I'm interested in. Do you guys use the box zoom? I hope you have. It's such a nice tool. You basically stretch, they call it a rubber band, which I feel is a little odd, but you stretch the upper left and lower right corners of a region, and then it fills up the screen with the area that you've just done. Well, that was kind of cool, wasn't it? I think I got to change the one function. The sine of x over x. Let's make it the sine of like 5x over x. I'll have to hit insert, put a 5 in there. That should make it look a little nicer. There's the negative of 1 over x. There's the positive of 1 over x. And here comes the trig function, zooming back and forth between those. In a scenario like what I've just set up, the upper and lower functions are known as the envelope, and the trig function, the sinusoid, was forced to lie in between the envelopes like that. And you can think about how that happened. It's this thing right here, the dividing by x. So the sine is always less than 1 in absolute value, so it lies between -1 and 1, and that forces the sine of any multiple of x over x to lie between 1 over x and -1 over x. Now, let's turn this into a sequence, or actually a triple of sequences. Oh, we don't want to look at it at that. Let me change the table setup so that it starts at 1, not 4. Why did I type 4? 1. And then we'll look at the table. Okay. So, oh, we can't see all three of them at once? That's bad. There's one, y3. y3 is our, the sine curve that I gave, right? And y2 and y1 are the 1 over x's. They're actually understandable. So if we can only see one of them, that'll be fine, because y2 is positive and y1 is just the same values but negative. Cool. So the first value in our sequence is negative 0.959, roughly. And that makes, that's in between +1 and -1, right? Then we get a negative 272. Should be moving this. Right? And then a positive 216. Then a positive 228. Well, this is a sequence. It's a collection of numbers. It's actually easy to compute what they are. It's just the sine of 5 times an integer divided by that integer. So, you know, the values are nice. Can we get any control over this function, though? This y3, look at how the values are behaving. Sometimes it's negative, other times it's positive, but moving around all the time. Is it approaching a limit? It would certainly seem not at first, especially this idea of sometimes negative, sometimes positive. That messes it up. But the squeeze theorem actually settles this very easily. So again, let's look at the graph. You see, that guy is stuck in between two functions, which can be reinterpreted as sequences at the natural number x coordinates, that are heading somewhere, aren't they? 1 over x, as x goes to infinity, that's going to 0. And so is the negative of 1 over x. 1 over x is a decreasing sequence, which has a limit of 0. So it's monotone, it's monotonic, it's monotonic decreasing, if you want to say that. Its lower bound is 0. I guess it has an upper bound too, because we're talking about from 1 off. So from 1 to infinity, that the highest value it has is 1. The negative of 1 over x, it's the same deal except sort of reversed. So it's an increasing sequence. It's monotonic increasing, and it's got an upper bound of 0. In fact, the limit value is 0. So that's where the squeeze theorem comes in. It tells you that if you've got a sequence which is trapped between two other sequences, and those other sequences are heading to the same limiting value, then your guy is squeezed in between them. And this is the picture you should have in mind. So I didn't make a scan of it. Sorry, I should have put I don't have the book handy right now, but the squeeze theorem is in this section in the book. I encourage you to look it up and read it. Look at the examples. This is a fine one. I think there's probably other examples that you can form, but it's surprisingly useful. It seems like it's got very strong hypotheses that you can find this upper bound sequence and this lower bound sequence that happen to both be heading towards the same spot. But I find that it's surprisingly often that you can find those sort of things, so you can make use of the squeeze theorem. Okay, so that's going to be it for today's lecture in the can. I'll see you guys. It's pretty late right now. It's almost midnight, back to 11:30. But hopefully everyone will get a chance to view this before class tomorrow, and I'll see you then.